Hello everybody and welcome to this channel about education and dissemination. Please remember that this channel publishes videos both in Spanish and English, and subtitles are available for both languages, so click the button if you need it. This will be an applied video. The aim of this video is to show you how to optimize a video for educational purposes when you are aiming to foster procedural learning. It will take as an example the resolution of an electric circuits problem, and after such explanation, I will end analyzing what makes this video a good educational tool for this type of learning, procedural learning. Though complementary, it also helps conceptual learning. One of my research lines is focused on the use of video-based learning to enhance the education in science, technology, engineering, and mathematics. And I am working together in this topic with Francisco Arredondo from Universidad Carlos III de Madrid. We are currently studying how self-created videos from students and a peer review strategy can enhance conceptual and procedural learning in an electrical engineering course. In one of my next videos, I'm going to deeply explain our research and our first results already published in IEEE Transactions on Education. But now let's focus on this video serving as an example of what is expected from the students in this activity. First, the course where this methodology is applied is electric circuits, and the objective is that they explain the resolution of an electric circuits problem on video. The objective of this methodology is to try to enhance their regular study homework routine, as well as their learning outcomes and academic performance. Let's provide an example of what is expected. Hello everybody! In this video we are going to solve this circuit that is being shown on screen. The objective is to find Ux, UR2 and Ig2 using Kirchhoff current law, Kirchhoff voltage law and Ohm's law. If we observe the circuit, we have a current source with 4 amps, two resistances R1 with 2 ohms and R2 with 2 ohms, and one voltage source of 2 volts. The parameters that we need to find are Ux, which is the voltage source, UR2, which is the voltage drop across resistance 2, and the current Ig2, which is the current flowing through this voltage source. So we can apply here the Kirchhoff voltage law. According to it, the sum of the voltages in a closed path equals 0. If we observe the circuit, in this area we have a closed path, path 1 for example. So we can apply here the Kirchhoff voltage law. So let's apply it. We have negative Ug2 as we enter the negative, because we are moving clockwise, and negative UR2 because we are entering the negative also. All of this equals 0. As we know the value of Ug2, we can write UR2 equals negative Ug2, which equals negative 2 volts. This is the first value, good beginning. But if we observe the circuit, we can see that this voltage source is in parallel with the resistance UR2. So the absolute value of the voltage drop, we knew that it should be the same. And this is what we have obtained, just considering that the polarity is inverse, so the sign of this magnitude is also inverse. 2 volts in Ug2 and minus 2 volts in UR2. We have 1/3 of the problem solved. Let's continue. What if we define a second path in this other part of the circuit? Let's call it path 2. We can also think of how the Kirchhoff voltage law would look like here. We start with negative Ux, then negative UR1, and then positive UR2. All this is equal to 0 because it is a closed path. In this case, we know the value of UR2 from before, but we don't know neither Ux or UR1. However, UR1 is easily calculable using Ohm's law, because we know the current flowing through the resistance, which is defined by Ig1. We have 4 amps flowing through a resistance of 2 ohms. Let's apply Ohm's law, which says that the voltage is the current times the resistance. Therefore, UR1 equals minus Ig times R1. This is UR1, minus 4 times 2, minus 8 volts. Then the application of this to the calculation of Ux is immediate with the equation we had from before. Ux equals negative UR1 plus UR2. Negative 8 plus negative 2, which is 6 volts. Cool! We have 2 of the 3 values set as objective in this exercise. We now know that Ux is 6 volts, and UR2 is minus 2 volts. Let's find the last value, Ig2. In order to calculate Ig2, we could use Kirchhoff's current law. We need to focus on a node, a point where 3 or more branches are connected. Let's choose this one, node A. In this node, we have incoming Ig current. Then we have another current, let's call it IR2. And then we have Ig2 in this third branch. Then Kirchhoff's current law establishes that the sum of currents entering or exiting a node equals 0. So let's apply it to node A. We can define that the entering is positive. Then we would have positive Ig1, negative IR2, and negative Ig2. All of this equals 0. We know the value of Ig1, but IR2 and Ig2 are unknown. However, Ohm's law can unveil the value of IR2, because we know both R2 and UR2. Applying Ohm's law at the resistance 2, we can write that IR2 equals UR1 over R2, which is minus 2 over 2, then minus 1 amps. So now we are able to calculate Ig2 using Kirchhoff's current law in node A. Ig2 equals Ig1 minus IR2, which is 4 minus minus 1. This is equal to 5 amps. With all this, we have completed the circuit. Knowing all the parameters of the given circuit is possible by the use of Kirchhoff's voltage law and also Kirchhoff's current law, as well as Ohm's law. They have allowed us to properly analyze the circuit and use the information received in order to calculate the missing parameters. Thanks for watching. And that was all. These types of problems are those given to the students for them to solve and explain in the videos like this one. And then, once the videos have been created, they are reviewed and corrected following a peer review methodology using the following rubric. The rubric evaluates 9 parameters, aligned with what literature defines as the parameters to consider a video of a good quality for educational purposes. Content structure and curricular alignment. The objective of the video is discussed at the beginning, and it ends also with a summary of what have we learned. Technical accuracy and completeness. To the extent of the aimed scope, the video has solved the problem clearly, concisely, and including descriptions of the methods used. Use of examples and linking concepts to prior knowledge. The resolution is contextualized, with mentions to the theory related to Kirchhoff's laws and Ohm's law. Rhythm of the explanation. The explanation is dynamic, and the tone and voice try not to be monotonous. Quality of the video. The audiovisual quality of the video is good, with proper illumination and good sound. Video length optimization. The length of the problem-solving explanation is efficient, not losing time in aspects that might not be relevant, but also not summarizing too much the content so that they cannot be followed. Content visualization, using auxiliary drawings, animation, or other resources. This video counts with visual aids as close-up, top view of the problem resolution while sharing the explanation through voiceover. Engaging communicative style. The communicative style can be considered dynamic and appealing. And this is all for now. This is an example of how a good didactic video for procedural learning can be made. I hope it has helped. If you like the content and think it could be useful both to you and to other colleagues, please subscribe and hit the bell so that YouTube can notify you when new videos are posted. Also, it would be really helpful if you click like, because then YouTube will share this video with more people. Every day brings us a new opportunity to learn. Are you ready?